In this last section of Chapter 5, we're going to compare power functions and exponential functions. And before we do that, though, we're going to compare power functions with other power functions. Now, to some extent, this is sort of a review from Section 5.1. We talked a little bit about dominance and how higher powers of x dominate lower powers of x. And so we saw that in Section 5.1. One thing that's new, though, is now looking at these power functions in the shorter term. If we look at the values between 0 and 1 and we look at different powers of x, you can see now that the lower powers of x dominate the higher powers of x in that little short run. So I don't know, maybe dominance isn't the right term. But the lower powers of x are actually greater than the higher powers of x. And it makes sense between 0 and 1 because you're dealing with little fractions like a half. And you know that if you square a half, you end up with a fourth. And if you square a fourth, you'd end up with a 16th. And so when you square fractions that are between 0 and 1, you get smaller numbers. And so those higher powers of x go to 0 faster as you approach 0, as they get smaller, right? Approaching 0 from the right-hand side of the axis. So let's take a look at the first example here. We have the graph of 3 different functions, and we want to first of all match the function with its graph. So we have x squared, we have x cubed, and we have 5x cubed. So the thing I would think about first is which one is going to grow the fastest. All right. Now the higher powers of x are going to grow grow faster in the long run, right? So which one of these graphs is growing fastest? It looks like A is growing fastest, right? Because at 1 we're already up at like 6 or so, and so this A is growing fastest. So it would seem that this function here would be A, right? Because it grows the fastest. Grows fastest. Okay, so then we have to decide between the other two, and that's a little bit trickier. But we can see that B is below C until we get up to like 2 or so. And then it looks like B is dominating C. We know that the higher powers of x always dominate in the long run, so then that means that this has to be B and then this would have to be C. And that's just because this B grows faster than x squared in the long run. All right, so now that we've identified the functions, let's take a look at this next question that says, do the graphs of A and B intersect for x greater than 0? And if so, for what value of x? Okay, so we're looking at A and C. All right, so we're looking at x squared and 5x cubed. Well, we can find any intersection points. Oh, sorry, A and B. Sorry, A and B. So it's 5x cubed and 1/2 x cubed. So we can find intersection points just by setting the functions equal to each other, right? Because we're looking for an x value where the y values are equal, right? So if we do that, we're looking for a value of x where 1/2 x cubed is equal to 5x cubed. All right. So, oops, not to the 5th cubed, right? All right. So now you might be thinking, well, I can just divide everything by x cubed, and you can do that as long as x isn't 0. One thing that I'd like to do is I could just subtract 1/2 x cubed from both sides. So I'd have 5x cubed minus 1/2 x cubed, which is essentially 5 minus a half. They're like terms, so we can just say it's 4.5 x cubed. Just write it as a decimal. And when does that equal 0? Well, it's only going to be 0 when x is equal to 0. So we can say no. These graphs will not intersect when for x greater than 0. All right, so let's look at the next part here. We want to know, do the graphs of A and C intersect for x greater than 0? All right, now A looks like it's growing very, very fast, and C is way over here. And from the graph, you can't tell anything, whether they're intersecting or not. And so, but let's do the same thing that we did before. Now we know A is 5x cubed, right? And we know that C is x squared, all right? So I'm going to do the same thing I did before. I'm going to move everything to one side and set it equal to 0, because I have to be careful about dividing by x, because x could be 0, and I'd lose that solution if I divide by x. So I'm going to do, so I'm going to subtract that. So it becomes what? It becomes x squared minus 5x cubed, which I can factor out an x squared, and I'll get 1 minus 5x. Okay, so I'm trying to figure out where those are 0, and obviously at 0 they're going to intersect, right? But there's another value where they intersect, right? If x is equal to 1/5, right? This is going to be 0 at x equals 1/5, right? If I put 1/5 in for x, then this factor 1 minus 5x will be 0. And so that tells us that, and that's a value greater than 0. So it tells us that the, well, they also intersect at 0, but I'm not really worried about that. I'm looking for values greater than 0. So, these two functions will cross at x equals 1/5. So yes, A and C intersect, oops, intersect at x equals 1/5, or I could write that as 1/5 and then put in the value of y that corresponds. I could give you a point, right? So the functions are 5x cubed and x squared, so it looks like 1/25 would be the y value. So they would intersect at this point, 1/5, 25th. Now obviously you can't see it on this graph, because unless I zoom in really close, you can't see that intersection point, given the aspect, the the graph that I'm showing here. I'd have to zoom in. All right, well, I'll meet you in the next video for the next example.